Hello, my name is Harshita and this is your Belmont Math Science Center tutor tip. Many students struggle with determining the solubility of compounds in water when given just the structure. So in this video, I'll show you why the structure is more than enough to answer the question. So first off, we'll start by defining some terms. So the first word is hydrophobic. Hydrophobic is basically hydro plus phobic, which is water-fearing. And hydrophilic is hydro plus philic, which is water-loving. And lastly, solubility is how well a compound can mix with a solvent. In this video, the solvent will mostly be water, unless I specify otherwise. And knowing what hydrophobic and hydrophilic means is important because, well, think about it. If something likes water, then it's going to mix well with it. And if something doesn't like water, then it's not going to mix so well with it. So something that's hydrophilic is going to be pretty well soluble in water, but then something that's something that's hydrophobic will not be as soluble in water. So I'm going to show 3 methods of how to use the given structure to determine solubility, and they're not like standalone methods. I usually use 2 or sometimes even all 3 of them together, but it's really just dependent on how comfortable and confident you are with each method and with your answer and the process that you use to get the answer. So the first method is the polarity test. So the mantra for the polarity test is like dissolves like. So that basically just means polar dissolves polar, and nonpolar dissolves in polar and nonpolar. Nonpolar dissolves in nonpolar. So you might be asking, okay, well, I can remember that, but what does polar mean? So polar is basically the presence of, well, 2 poles that have opposite charges. And you can determine the polarity of a bond based on the electronegativity of the atoms that are in that bond. So in this diagram over here with the periodic table, you can see that there's like little numbers below each of these elements. And you can't see all of them because I didn't make it big enough for you all to be able to see it, because the point isn't that you're supposed to memorize the numbers, because that's a lot of numbers and it's kind of pointless to memorize them because no one's gonna, it's not really beneficial to memorize all of them because there's just no point. If you were given a table with these elements and their electronegativities with them written below them, then you can use those numbers and this one other thing to determine if something's polar or not. But you won't always be given a periodic table with that. So a better thing to do is kind of understand the electronegativity trends and how the difference in electronegativity affects polarity. So the trend is that electronegativity increases as you go this way, so from left to right, and also from bottom to top. So whatever's in this top right corner, so fluorine, has a very high electronegativity, and something that's in the left bottom left corner, so this Fr, I think francium, I don't know, has a very low electronegativity. So you can remember that trend. And another good thing about organic chem is a lot of compounds that you come across in organic chem have the same types of bonds. So there's CH bonds, OH bonds, NH bonds, and CO bonds. Those are the most common bonds. And you will come across other types of bonds. So there's HF or HCl or CCl or stuff like that, but that's one, less common, and two, it's also not that much harder to learn those. But anyway, what I'm trying to say is, since there's only like a handful of bonds that you need to memorize, it's very easy to kind of memorize which ones are polar and which ones are not. So CH for one is always non-polar. So sorry, I took a gap there. I was trying to say, um, there is like a very slight polarity, but it's too small for them to be considered a polar bond. So that's why they're non-polar. But OH, on the other hand, they are very different. So like you can see that H over here is lighter green, and O over here is a very much darker green, whereas C and H are pretty close to the same shade of green. So that's why O and H are like super polar bonds, which you can tell by the fact that water is pretty polar. So just memorizing kind of the general trend of bond polarity is a good idea. But even otherwise, you can just think, well, CX, like when I'm saying like CCl bonds, well, C is all the way over here, like in the periodic table. Like if you didn't have numbers over here, if you just had a normal periodic table, it would be C is over here, and Cl is all the way over here. And that's kind of a pretty far distance. So maybe that would probably mean that the electronegativities are also quite different. So it would be a good bet to place that they are polar. And in reality, they actually are, because they have an electronegativity difference of 0.5. And if you have a 0.5 difference, then the bond is polar. But yeah, so like just having that general, that type of general understanding of the concept of electronegativity could be really helpful when you're doing the polarity test. So that's what I wanted to say about polarity. And over here I have kind of like a little cartoon that I'm sure most of you have seen, where the hydrogens, or not the hydrogen, sorry, the water drops are approaching an oil drop, and they're like, come on, let's hang out. And the oil drop says no, and the water drop starts calling it names. So I just wanted to show this cartoon as an example to explain why that happens. So what happens with, well, let me rephrase this. A compound being polar is important because if you're polar, then it means you have like a slight positive and a slight negative charge on either ends of the molecule or compound, and that would mean there would be some like dipole-dipole interactions and attractions happening. And specifically with water, since there's hydrogen involved, there's going to be hydrogen bonding that's going to be happening. So if you look at this diagram over here, you can see that there's like an OH, and there's like OH bonds, and that's pretty much all there is in water. You can also see like little red dots between O's and H's over here and over here. And since we just established that O and H is a polar bond, we can see that the H's and O's are getting attracted to each other through hydrogen bonding, and they're kind of like sticking together, and they're mixing well with each other, which is why you can pour, like, if you have like two glasses with some amount of water, and you pour glass 2's water into glass 1, all the water is going to mix up really well. You're not going to see a difference because water mixes well with water. But if you look at oil, on the other hand, you can see that it just has a long chain of carbons and hydrogens, and we established this as well, that the carbon-hydrogen bond is not very polar. So according to this mantra or like itself, like a non-polar compound would not mix with the polar compound, which is why oil does not mix with water. So method 2 is the method that I personally like the most, is counting polar groups. So the rule in that one is an organic compound is soluble in water if there's at least one polar group for every 5 carbons in the compound. And for this specific kind of rule thing, the polar group is considered in a bond, like a hydrogen bonding with either an oxygen, nitrogen, or fluorine. Okay, so that basically just means if you have at least one of those OH, NS, NH, or HF groups in a compound for every like 5 or less carbons, then that compound will be soluble in water. So here's some examples. Here there's one polar group, and there's also just one carbon, so there's enough, and it's soluble in water. It's like very soluble in water because there's only one carbon where there's like a whole polar group in here. But in butanol, you can see that there's 4 carbons, and there's a alcohol group, but it still satisfies the rule because you need to have one polar group for every 5 at least. And there's only 4, so you're still good. So it's still soluble in water, but it's less so than methanol because, again, there's slightly more carbons here. But then you look at octanol, and there's 8 carbons for one polar group. So that means there's 3 extra carbons. So this won't be soluble in water because it's too, well, the reasoning behind it is that it's too non-polar, even though it does have a polar group, because a majority of it is composed of non-polar bonds. So that's how that works, and I just really like this method because it's kind of like pretty straightforward and almost like set in stone, kind of, although there's always exceptions. But this one's pretty like concrete, so you just count up the polar groups and count up carbons and be like, okay, this is soluble or this isn't. Like, it's pretty straightforward. There's not a lot of confusion that's gonna occur when you try doing this method or using this method. So the third method is using functional groups, and honestly, this was something I didn't know until recently. So I think it would be helpful if you guys knew it now and when you guys still are in organic chem. So the ability of a compound to participate in hydrogen bonding is key to water solubility, like I showed in the oil and water example. So again, a compound can hydrogen bond with water when it's polar, and it can be polar only when there's like differences in electronegativity. So, and like there's functional groups or specific groups that have specific structures. So keeping all of that in mind, there's a couple of kind of conditions that can make a compound more soluble in water compared to others, and this is kind of a list of those conditions that I found in a website online that I can link in the description if any of you guys want to go through it. And it's listed in order of importance or order of effectiveness if you want to take it that way. So the first one is anything with a charged group is almost certainly water soluble unless it has a very large nonpolar group, in which case it will most likely be in the form of missiles like a soap or detergent. So that basically just means if there's a charged group in your compound, like if it has like a positive charge or a negative charge or whatever, then it's going to be soluble in water, unless it also has like a really big non-polar group, like, so let's just say a really big hydrocarbon chain. So it says it'll form in missiles, which I'm not sure a lot of you know, so that's why I put in like this little cartoon over here. And I was going to take the opportunity to explain what soaps do. So a missile is basically something that has it's something that has a hydrophobic and a hydrophilic side. So in this example, there's some grime that's stuck to, let's just say it's stuck to the floor, or actually, you know what, it's soap. Let's just say it's stuck to the skin. So there's some grime stuck to the skin, and you can see that not all of like the dirt or oil or whatever that is on your skin or hands gets washed off when you just wash it off with water, right? So you use soap because soap has a hydrophobic and hydrophilic side. Water itself is polar, and the grime is usually non-polar. So polar and non-polar don't mix, which is why they don't wash away. But soap, since it has a hydrophobic and hydrophilic side, the hydrophobic, which is the tail, it can kind of attach to that grime, and then once it's like fully surrounded it and gotten a good hold of that grime, it can kind of air quote call water and be like, okay, well, we got this now. I'm ready. Let's keep going, and the water will kind of um, the water will attract the hydrophilic head of the soap, and it will just wash away the soap that has the um, grime that is kind of enclosed inside it in a way. So that's what it means when it says it'll mostly be soluble in the form of missiles, where some part of it will be soluble, but the other part won't. So that's the like first priority kind of thing, or highest solubility. Sorry, not first priority, but highest solubility condition. The second one is any functional group that can donate a hydrogen bond to water. So that would be alcohols and amines. And being able to donate a hydrogen bond is, I guess, in the simplest way to say it would be if it has the hydrogen attached to the polar group. So, like I said before, the OH and NH groups. So if you have like the OH and NH and HF group anywhere, then it means that you have the potential to donate a hydrogen bond, which will make it possible for for that compound to be soluble in water. So it'll like increase the solubility of it. It's what it's saying over here. So the third condition is any functional group that can accept a hydrogen bond from water. And the examples were ketones, aldehydes, and ethers. And it says they have a somewhat smaller but still significant effect on water solubility. So accepting it basically just means you have a polar group, but it's not a polar group that has a hydrogen in it. So it could be like a CO bond, which is what is happening in all of these. So ketones and aldehydes have a carbonyl group, which is a C double bonded to an O, and an ether has, well, kind of the R groups attached to either side of the O. So that would make ketones, aldehydes, and ethers also quite soluble in water, but not as much as alcohols and amines or charged groups. And then the last one is any other group that can contribute to polarity. So alkyl halides, thiols, sulfides will make a small contribution to water because although they are polar, which according to the first rule, polar dissolves in polar, would make them dissolve in water, but to actually like be completely miscible in it, you need to be able to do hydrogen bonding. And like for alkyl halides, for example, the polar group is the C bonded to a halogen, and there isn't possibility for hydrogen bonding to occur because there's no hydrogen in that polar bond. So that would make it a little hard for it to be completely miscible in it, but it would dissolve to some extent in it. So yeah, so those were the three methods of functional groups. Three methods of determining solubility of a compound in water based on structure. That is all that I had. Thanks for watching, and hopefully this was helpful. I think if I had something like this when I was in organic chem, or even gen chem really, I would have really liked it. So, I hope you guys found this useful or informative. But feel free to contact your professor or stop by the Math Science Center if you have more questions, and we'd be very happy to help. Thank you for watching.